unSILOed podcast is produced by University FM, elevating the stories of your institution.
Welcome to unSILOed. This is Greg LeBlanc, and I'm here today with Kit Yates, who is a professor of mathematical biology at the University of Bath in the UK, and also the author of a couple books. Most recent book is called How to Expect the Unexpected, The Science of Making Predictions and the Art of Knowing When Not to. And his previous book is called The Maths of Life and Death, Why Maths is Almost Everything. I'm guessing this must have had a different name in the US because
you've got the UK copy there, but yeah, it's The Math of Life and Death in the US version.
Yeah, right. We talk about math in the singular. Right?
Sure, exactly.
In the plural. But you know what's interesting about both these books is that there's remarkably little math, right, as we think about it. You know, in terms of formulas, right? So you've got a whole chapter on, Bayesian updating, and the Bayes rule is never in the chapter.
No, it's completely deliberate. I don't want to put people off with equations because that, for me, is not really what maths is about and not really what I want to do with the books. I want to make people aware of the places where maths can have an impact on their life and to give people tools and tricks and tips that they can use based in mathematics. But actually some of the tools, for example, that come out of Bayes' theorem, you don't need to know the mathematical formula for Bayes' theorem to understand the lessons that it can teach us for reasoning and for making decisions and for predicting the future. My aim is to not scare people off with equations because I think it does put people off. I think Stephen Hawking suggested that you halve your readership with every equation you add into your book. So I tried to follow that principle.
Yeah, well, there's two comments that you made in the books. One is that, we are doing math all the time, right? So when you're debating whether to cross the street, to beat the truck that's coming in your direction, like you are doing math, right? You are assessing probabilities. Right, you're calculating trajectories and so forth. Yeah. So you're doing math. I mean, animals do math, right?
Right.
Ants are doing math, and penguins are doing math. I mean, we're all doing math all the time.
Yeah,
The second thing you made is that we think, however, of math in the form of stories and narratives, right? And so when I teach my stats classes, I mean, we obviously have formulas and so forth, but the bulk of it is made up of stories, and that's sort of how I think most people encode the mathematical structures that they live by is primarily through narratives and stories, and so I like that piece.
Yeah, I think certainly what I'm not trying to claim is that a dog catching a frisbee is solving a quadratic equation or doing calculus, but we're using heuristics. When you sing to yourself in the shower, you are appreciating, you're hearing mathematics writ large. That's sort of what music is about. It's about mathematics turned into art. We're seeing the products of mathematics all around us all the time. I think that I wanted to share that through the medium of stories because that people connect with that. I wanted to tell the stories of real people's lives where they've been impacted by mathematics, perhaps without even being aware of it, so that other people who read the book can then be aware of what's going on and spot those situations when they start to come up.
Mm-hmm. Now, in the most recent book, you're talking about forecasting and prediction, and you start off the book in a very unusual way because you talk about going to see a psychic. And, a lot of books when they talk about whether it's heuristics or the psychology of how we interact with the world, they emphasize the ways in which we make mistakes. And I think you do a lot of that in this book. But I mean, by highlighting the mistakes, of course, you're also highlighting how most of the time our forecasting works pretty darn well. And then you are emphasizing sort of the mismatches, right, on the boundaries when it doesn't work so well. So why did you decide to start off by going to a psychic?
So what I wanted to understand is nowadays we have some really great scientific methods which allow us to predict the future. We use maths, we use science or math, and we can predict the future by building models and running them forwards in time, or we can make decisions about what's currently happening, or do what's called nowcasting instead of forecasting to find out what's currently happening in situations where we don't have the full picture. But we've relied on the development of these sophisticated tools, and what I wanted to understand to start the book off was how did seers and mystics and soothsayers and oracles back in the past who didn't have access to these scientific tools, how did they seemingly predict the future or get things correct without having access to these scientific tools? And the closest thing that we have to that today, I think, are psychics who try to convince you that they know something about you, about your past, about your future, without being told anything about it. But they don't use scientific tools to do that. They use a whole bunch of psychological manipulations to make you think that they know something about you, and to give you the impression of being accurate about their predictions. And so I went to this psychic to try and see what these tools and techniques were, and to see how they would be used on me and whether they would be effective.
Well, do you think we all carry around within ourselves our own inner psychic, right? Where we convince ourselves that we are, better at predicting the world than we actually are?
Yeah, and I think there's a phrase that I often use, which I think it's better to be aware of the uncertainty. It's better to be uncertain about a prediction than it is to trust 100% in a poor prediction. And this is sometimes what we do. We are so convinced that we're right, we fail to check the possibility that we could be wrong. We fail to ask that question, what if I'm wrong? And actually we can get into trouble with that. And it's much better to be uncertain and to admit and to acknowledge that uncertainty about a particular prediction than it is to be 100% certain with the risk that prediction is wrong. But it's difficult for us to do because it relies on us having this argument in our head, which many of us don't like to do.
Yeah, why are we so averse to uncertainty, right? Why is it that we, crave the illusion of certainty when it obviously can be dysfunctional in so many ways?
Yeah, absolutely. Yeah, we long to have a single path to follow. We don't like it when there's a fork in the road and we have to make a decision. We're not good at weighing up probabilities, particularly, I think. So actually putting numbers on, which path is the right one to choose, which decision is the right one to take. And we tend to binarize. So we tend to say yes or no, to say 0 or 1, and try to make a decision about that. Whereas actually we should be saying, well, actually this path might be right with 55% probability and this one with 45% probability, and then assess what we should do based on that. But yeah, we're not good with dealing with probabilities, I think, is one of the reasons why we like to binarize. For the weather forecast, for example, even now when the weather forecast comes with a probability of precipitation of 75%, in my head I will say it's going to rain, so I need to take my coat. Even though it's only 75%, or if it's 20%, I'll be surprised when it doesn't rain. When it doesn't rain, because I am expecting it not to rain. So I'll be surprised if it rains. But even though it said, 1 time out of 5, it's going to rain in this prediction. We tend to binarize and tend to reduce probabilistic decisions down to yes or no, 0 or 1. And I think that's part of the reason why we struggle with uncertainty.
Yeah, and you had some interesting comments on kind of communication, right? So if we respond to objective forecasts in a way that is inappropriate, does that make sense then to provide forecasts that are, skewed in the direction that will result in appropriate behavior? I mean, that I found that fascinating about weathermen, right? So that, weathermen are aware of the fact that we look back on those forecasts, right, retroactively and in ways that are inaccurate. And so then some of them will skew their forecasts to kind of minimize the likelihood that we take the wrong action or that we, retroactively remember their forecasts incorrectly.
Yeah.
I mean, that seems, we saw that, of course, with COVID, right, where the communication of risk becomes an ethical question.
Yeah. Firstly, weather forecasters, I think, get a really hard time. I think they have an unfairly poor reputation. Part of the reason for that is sort of availability heuristics. We remember the times when they get things wrong. We remember the time when For example, in the UK in 1987, we had a very famous incident where weather forecaster Michael Fish came on, and he said, "We've had some calls to the BBC suggesting that there's going to be a hurricane in the south of England tonight. Don't worry, I can assure you there won't be one." And then we had the worst storm we'd had for 100 years, and people died as a consequence of this. And so, we tend to remember those single instances where we get it dramatically wrong, or even when the weather forecaster says it's not going to rain and it does rain, and we remember that because we get wet and it annoys us, right? Whereas the 6 days out of 7 when they predicted rain and we took our umbrella and we didn't get wet, then we forget those days. And so this is why, as you suggest, weather forecasters do sometimes exhibit what's called wet bias. So they over-predict the chances of rain. Their model will predict 20% and they'll say 30% to give people a push towards the likelihood of taking their umbrella, to make sure that they don't get it. Because people aren't so annoyed when they prepare for a situation like taking an umbrella. When it's not raining, no one really complains too much. It's just the weight of carrying an umbrella. It's not a big problem. Now
they're probably happy. They're like, "Oh, it's great." Like,
yeah,
"Oh, great.
Yeah, it's fine.
Weather forecaster
it's
wrong.
fine. Like,
Wonderful."
it's not. Yeah, exactly. When the weather forecaster's wrong in the right direction, then it's perfect. But you touched on the idea of COVID, and this is a really interesting. Has really interesting ethical implications, because I think the precautionary principle would suggest that we should have perhaps acted sooner in some cases to suppress the spread of COVID and to avoid bigger waves. It would have saved more lives. But there's a balance to be struck, because, of course, by taking these measures that we took, I think, for example, closing schools or whatever it was, those measures potentially have impacts as well. And so we have to weigh those up. It's not like there's zero consequences for the weather forecaster who overpredicts rain and there is no rain. That's no problem for that. But if you overreact in this context, then there are consequences. Maybe you could argue they're not as bad as the consequences of what would have happened if we had not acted, or acted even later. So that does argue for the precautionary principle. But there are ethical judgments to be made on that, and we can't move away from that and pretend that there aren't.
Mm-hmm. Well, there's the interventions, and then there's the communication of risk, right? So, if you say we don't know the risk and we're going to err on the side of caution, that's different from saying, here's what we think the risk level is, when it's actually, perhaps lower than what it is.
Yeah, absolutely. And I think something that I've been trying to do when I've been communicating around science, around COVID, is to try to acknowledge the uncertainty that's associated with predictions. It's very tempting for us to look for a single number. For example, what's the prevalence of COVID? We have a really good survey in the UK. The Office for National Statistics ran a survey, the COVID infection survey, which told us each week what proportion of people were infected. And the headline figure was always, it's 2% or it's 3% or whatever. But actually, there's uncertainty associated with those projections. Those are not predictions, if you like, but they're these sort of nowcasts that I was talking about earlier. And there's uncertainty, and so there's actually a confidence interval which suggests how likely it is to be higher or lower than that. And it's important, I think, to communicate that uncertainty, to show that actually maybe we don't know exactly where we are. Maybe we do. Maybe the uncertainty bounds are really tight, and so actually we're really confident. But if we're not so confident, then we need to communicate that as well.
Yeah, I always thought COVID was a fantastic opportunity for public instruction in probability, statistics, and math. I feel like it was
absolutely.
a big missed opportunity. We got all these people sitting at home. We could, because people were talking about things like R-naught. People were talking about, VIR, SIR models. People were talking about exponential growth. But I don't think that we did a good enough job of really explaining this stuff, right? Because there were so many misconceptions and misunderstandings, and it seemed like, media people would just kind of glide over, sampling bias and stuff like that. Did the public kind of communicators of math kind of miss their best opportunity to shine in the limelight during those 2 years?
Yeah, so I'm mixed. I'm mixed about it. I think it was a great opportunity to communicate math and science, and I think there was a lot of that about if you knew where to look for it. But it was never really adopted in a sort of mainstream where you, I mean, it was interesting because we were talking about the reproduction number R on the news in a way that I never thought we would. Like, so I wrote the Math of Life and Death. It came out 3 or 4 months before the pandemic, and the last chapter in the American version of the book is called How to Stop an Epidemic. And so, yeah, I covered all these concepts like R0, infection fatality rates, case fatality rates. I also have a whole chapter on exponential growth in there. And so, yeah, I mean, when the pandemic struck, I tried to get out there and communicate, but, you know, I have a limited platform. And occasionally I was invited on the news, and that was great. And I could actually try to talk about these mathematical concepts. But I think where we really lacked this scientific understanding was perhaps in the political sphere, where many of our politicians didn't understand things like exponential growth, didn't see what was coming around the corner. Even when we had examples from countries which were already being impacted, we still didn't take on board the mathematical models. And interestingly, in the UK, we're going through our COVID inquiry at the moment, trying to learn lessons about that. And clearly, some of the mathematical models that were presented to the politicians were not believed, if you like. And I don't know whether that's due to scientific illiteracy or something else, but certainly we have a missed opportunity to educate our political classes as well as the general public.
Well, you talk about how we think naturally in linear terms, but so much of the world is exponential. You also say that, you know, we think more naturally in terms of kind of negative feedback when so much of the world has, you know, positive feedback. Why do you suppose that is? I mean, is that sort of ecologically rational? I mean, is there, you know, were things like positive feedback and exponential growth more rare in our everyday experiences in the past than they are today? I mean, I certainly think in the world of business, positive feedback seems to be more important than it was in the past with, you know, network economy and so forth. But just in terms of our natural experience of the world, why do we have so much trouble with things like exponential growth?
Yeah, so there's definitely a preponderance towards what's called linearity bias, right? So to explain linearity bias, I should explain what a linear relationship is. It's a relationship between two variables, an input and an output, where the fixed change in an input will give you a fixed change in the output. So if I'm changing pounds into dollars, for example, New Zealand dollars, because it's an easy exchange rate of 2 to 1, let's say, not US dollars. But if I change £20, then I should get back 40 New Zealand dollars. Now, if I increase that by a fixed amount, if I want to change £40 instead, then I should get a fixed increase in the amount of dollars I get back. I should get $80 back. And again, if I increase from £40 to £60, I should increase from $80 to $120. And when you draw this on a graph, if you draw pounds on the horizontal or x-axis and dollars on the vertical or the y-axis, then I should get a straight line. And that's why they're called linear relationships, right? Because you get a straight line on a graph. Now, that one is a particularly special type of linear relationship. It's called direct proportion, which means that for no pounds I should get no dollars. When I double the input, I should double the output. But not all linear relationships are direct proportion. For example, the change conversion between Celsius and Fahrenheit is a linear relationship. Every degree Fahrenheit is worth 1.8 degrees Celsius. You get a straight line when you draw it on a graph. But it's not direct proportion. You don't just double, when you double the Celsius temperature, you don't just double the Fahrenheit temperature. So that's linear relationships. Now, what I argue in the book is that many of the most important phenomena in the world that we experience are non-linear. All sorts of different types of non-linear relationships. So it could be exponential growth, where something is growing in proportion to its current size, which is a special example of a positive feedback loop, where something grows or decays in proportion to its current size. Or it could be a square relationship, like the ratio between the area of a pizza and its diameter, right? So these non-linear relationships are there, and they confound us because we're not used to them. And the question you were asking is, why are we so ingrained with this linearity bias? And I think the answer is that for generations and generations, things have stayed pretty much the same, or they've changed at a roughly constant rate. Back in the day, many of us would have expected to have done the same job that our parents would have done, to have the same role. Things didn't change so quickly, and now in modern times that really isn't the case. For example, we're talking about relatively recent innovations like the stock markets, for example. You see all sorts of non-linear feedbacks coming in there, which mean that things don't behave in the way that we would expect them to. And so, we have this ingrained linearity bias, which is associated also with another type of bias called normalcy bias, where we expect things to just carry on as they are, which means that we react slowly or too slowly or poorly to sudden changes, catastrophes, disasters, COVID-19 pandemic, for example. And so, these things are all interlinked, but I think it's just, the pace of change has been relatively slow for much of human history, and nowadays that's not necessarily the case.
So the normalcy bias, it's kind of what we call them sticky priors, basically. So new information does not lead you to adjust your understanding of the world. But sometimes, of course, you over-adjust, right? So, how do we become better Bayesian reasoners without understanding Bayes' rule?
Yeah, so I think there are three main lessons that Bayes' theorem can teach us. So Bayes is about how we change or update our opinions based on new evidence, right? So when a piece of new evidence comes in, how do we react to that? And often there's a temptation when we've already formed an opinion to ignore a piece of new information, right? It's typically what we would consider confirmation bias. We either don't look for new information which contradicts our current opinion, or what's called our prior belief in the Bayesian sort of world, in the Bayesian format, or we see that information come down our Twitter stream or whatever, but we ignore it because we don't like it. It produces some sort of cognitive dissonance inside us, and we don't like to take it. We like to binarize, and we like to say one thing or the other, but if there's something that's ambiguous, we don't like that. So what Bayes' theorem does is it provides you a way of updating your beliefs in the light of new evidence. But the three main lessons, without going into the mathematics, that I think you can draw from it are, firstly, that new evidence isn't everything, that we shouldn't forget that we had prior beliefs about this subject before a new piece of information, no matter how sort of in our face it is, how revelatory it seems to be. We had prior beliefs, and we shouldn't completely throw those away and just adopt this new piece of evidence as the only piece of evidence on the subject. However, to throw that backwards, you also have to change your opinion incrementally when the new evidence comes in. So that means you can't just ignore a piece of new evidence as it comes in. You need to change your opinion incrementally. It's tempting to ignore small pieces of information which contradict our favoured opinions. But if you ignore every piece of new evidence that comes in, then eventually you end up trying to hold back a rising tide of evidence against your opinion, and when that tide becomes too strong, the barriers break, then you have to flip-flop your opinion. You have to do a dramatic 180 reversal of your opinion, and this is often what I think happens to politicians, is they wait and they hold their opinion because it looks bad. They think it looks bad for them to be changing their opinion, and then they have to do a dramatic flip-flop and change their mind. And actually really what we ideally should be doing is changing our mind as new evidence comes in. And then the last piece of advice from Bayes' theorem is that we should try to embrace uncertainty. And this is really difficult. We've talked about this already, this idea that we like to just have a clear answer, 1 or 0, yes or no. But actually it's a spectrum, it's shades of grey, it's not black or white. And actually, if you hold an opinion with 100% certainty, then you can never change your mind, no matter what evidence comes in. If you're 100% certain as your prior, this is your sort of sticky prior idea, then you can never update your opinion. So you need to have that uncertainty. Even if you're really confident of an idea, you need to be able to accept the possibility that it might be wrong. And this is where we came into such grief in the pandemic with people like anti-vaxxers, for example, who have already made up their mind about one thing, vaccines don't work, and then they will search out evidence to support that idea. climate change is another example. We have climate change deniers. No matter the weight of evidence they're presented with, they've already made up their mind. So there's almost no point arguing with these people because they've already made up their mind in many of these respects. And I would argue, to make good decisions, to not get things wrong as often as possible, you need to acknowledge and appreciate uncertainty around issues.
Well, now both these books are targeting sort of a general readership, but I mean, it seems like the insights that are in the books, I mean, everyone needs to be reminded of them regardless of who they are. I mean, I know people who are really good at various econometric methods, right? You know, and they can put fixed effects in their models, and they can transform all the variables and so forth, and they can do all this complicated stuff, but they often will, you know, overlook some of the more basic insights around probability, resulting in things like p hacking. I mean, if sophisticated scientists can sort of forget about the basics of inference, I mean, what hope is there for the ordinary person? I mean, do you think that where is it more dangerous for people to kind of lose track of good inference and forecasting? Is it more dangerous for the ordinary people to kind of get it wrong, or is it more dangerous for the scientists and the experts to get it wrong?
So it depends what the context is, right? It also depends what you mean by ordinary people, right? Like, if our politicians, who are just ordinary people, non-scientists, are making these sorts of mistakes, and that can have huge consequences for everyone in that country or even across the world. I think for me, I have been sort of humbled by the books or the process of writing the books, because I sort of thought I knew much of this stuff beforehand, but actually, you know, having it reinforced for me and you know, realizing situations where I probably make these sorts of mistakes myself. I'm not going to try and put myself on a pedestal. I'm not trying to say I'm the sort of perfect forecaster or decision maker. I make these mistakes as well. I make assumptions when I see coincidences. For example, I jump to conclusions when actually it's probably just randomness at work. I do this thing where I look at the weather forecast and I binarize. Like, I try to tell myself not to do that, and I'm maybe slowly getting better, but I do this, and certainly before I wrote the books I do. And everyone makes these sorts of mistakes. But yeah, I mean, I think the point of writing the books is just to highlight the places where you might find these sorts of mistakes. So there's the Texas sharpshooter analogy, where this guy goes out into his barn and he shoots a load of holes in the wall when he's drunk, and then the next morning he comes back and he draws a target around some of the holes that happen to lie close together, and he says, look what a great shot I am. And if you're only showing the target, then you think, yeah, fine, this guy was a really good shot, he hit the target every time. But then you're showing the whole of the barn wall, then you realize that actually it's just randomness. And this happens in real life. And one of the stories in the book is about a group of concerned parents who mark out cancer cases in Omaha, and they find a cluster of them which are close to a group of power lines, and they go on this search for trying to find out and trying to tell the government there's these power lines that are causing cancer. And actually there's no evidence to suggest that power lines cause cancer, and there's been big studies that have been done to suggest that that's not the case. There's no sort of physical scientific method by which power lines could cause cancer, and actually it's just this Texas sharpshooter. They just found a cluster close to power lines, and in what could just be random case data spatially aggregated across the city, and drew a conclusion based on that. So I think it's useful for people to know the places where these can come up, for everyday people, for the lay public, if you like, but also, for scientists as well, but for politicians too, because they're the people who are making the decisions which often impact on us so strongly.
Yeah, and I think it's also very difficult to evaluate the accuracy of forecasts, because we don't always have access to the data that would enable us to drop a confusion matrix, right, ex post, and also because of what you call the I guess it was the prophet's dilemma, right? If people actually respond to your forecast. I mean, if you say, hey, we've got this terrible thing coming and everybody needs to take action to prevent it, and everybody takes action to prevent it, and it doesn't happen, then people, they'll never know whether you were right or wrong, right? And so this is the dilemma, I think, of the risk manager at big banks and other firms. If they never get rewarded for the disasters that they were able to, avert through their action. They just, they just generate resentment when people are when they're telling people not to do stuff, right?
Yeah, that's right. Self-defeating prophecies we're talking about, right? Interestingly, I think weather forecasting is a place where you can get really good analytical data on how well your forecasts fared compared to the actual data that transpired, and you can do it over and over again on different days. But yeah, generally, I think there is this prophet's dilemma, which is an example of a negative feedback loop, which is something where you make your prediction, and then the results of that prediction end up going against the thing that you were predicting. So, for example, with COVID, in the UK. There was an article in October 2020, so 6 months into the pandemic, which said one of the biggest COVID data failures was the modelling at the start of the pandemic. It predicted 250,000 people would die if we carried on the same course, and that manifestly didn't happen. And of course, as soon as that model came out, this was a famous model from the Imperial College Modelling Group, the government were almost forced to act, because how could they let 250,000 people die? It became a self-defeating prophecy. But of course then detractors of mathematical modelling said, well, the models were wrong. And actually there's no reason to believe anything different, especially given already in the UK we've seen almost 250,000 COVID deaths. So it's the prophet's dilemma. It's dangerous to make your predictions too accurately, especially if they can influence the outcome of the prediction. Yeah.
Now, I teach a course called Statistics for Business, or sometimes something like that, and I was always curious, because we have statistics for biology, we have statistics for business, we have statistics for lawyers, and it seems like, I mean, there are pure statistics courses, but a lot of people would say that if you want to teach sort of quantitative reasoning, you want to teach it in sort of a domain-specific way, right? With examples that are drawn from the discipline. I mean, why do you suppose that is? I mean, is it because people find it difficult to map over abstract mathematical principles from one domain to another? I mean, when I teach statistics for business, I bring in examples from biology and all sorts of other disciplines. But I think there seems to be this belief that there's something about the domain in which you're operating where these mathematical ideas need to be grounded. Have you experienced that? I mean, when you teach mathematical biology, I mean, do you typically use examples from biology, or do you draw from the same examples you use in these books, like on Ponzi schemes and so forth?
It's a super interesting question, because as mathematicians, and that's probably what I would see myself as first, I was trained in mathematics at university, and didn't get into math biology until a little bit later. As mathematicians, this is exactly what we do. We sort of forget about the context, and we look for the patterns, the key processes which are common to all of these sorts of processes. And when you can start to spot them across different disciplines, that's when you know that you've got something which is close to truth, or close to something which is underlying a common phenomenon which is underlying many of these systems. When I teach mathematical biology, I actually teach a course called Modelling and Dynamical Systems, and so in that I draw from all sorts of different models, some from biology because they're quite amenable and people can sort of get a feel from them, but some from sort of even like waste management, all over the show, all different examples, because I'm trying to show that maths can be used to represent all sorts of different processes in the world. But I can understand why people want to put the maths that people are learning in this sort of siloed context, if you like, in this context of the subject that they're teaching, because people like to, when they're learning, they like to bridge from one island that they know about to the next island. So if they already know about the biology, then it's nice to make a bridge to the mathematics which contains the biology, I think. So we like to jump from island to island over these bridges, rather than just flying halfway around the world and just saying this is maths in an abstract concept which you're not familiar with. Eventually, though, what we would like is for people to, at least as a mathematics teacher, for people to be able to see these patterns that come up in different disciplines, and to be able to spot them when they appear, and to abstract, for example, things like exponential growth occurs in radioactivity, it occurs in biology, it occurs in epidemiology, it occurs in all sorts of places, and the fundamental process that's going on is something is growing in proportion or decaying in proportion to its current size. And that's what mathematical modelling is about abstracting away the detail really and turning it into a mathematical formula. So yeah, there's a difference between mathematics for mathematicians and mathematics for people who need to use it in their subject specific area, I suppose.
Well, do you think that the sort of ordinary person needs to know more math now perhaps than they did in the past? I mean, are we making more decisions in our everyday lives that are dependent on math? I mean, you start off the book, I forget which one it was the Maths of Life and Death, where you talk about a Ponzi scheme, right? And, I mean, this is something, I mean, presumably people are encountering Ponzi schemes all the time, right? I mean, they're being seduced by erroneous math on a fairly regular basis. I mean, and they need to be able to guard themselves against that.
Yeah.
Do you think that people who are math illiterate are in some ways more vulnerable now than perhaps they have ever been?
Yeah, so again, what I would suggest is that I'm not suggesting everyone needs to have degree level mathematics or even like top end high school mathematics. We don't need to be mathematical geniuses, but we need to be aware of the places where mathematics can have an impact, and those, in response to your question, those are the places those are increasing in frequency over time. We're increasingly presented with more and more data. For example, you go to the doctors and you're told there's a whatever % probability of you having this disease. You need to know how to interpret that, and you also need to have the confidence to question your doctor about what that means, and to ask them to try and help you to interpret those statistics if you can't interpret them for yourself. In the first book, in Maths of Life and Death, there are examples about screening and understanding the results of screening tests, and often, and it's been shown through sort of psychological and scientific studies, that the doctors who are presenting the results to us don't always have the best understanding of the mathematics that is underlying these screening tests. So unfortunately we fall victim to what's called the illusion of certainty, where someone presenting a number, we see them with authority, and we see numbers as sort of small hard nuggets of truth that are irrefutable and that we can't question. And actually what I would advocate is not that we all need to be doing differential equations or anything like that, but that actually we need to be questioning this illusion of certainty that comes with authority, that comes with numbers, and asking for interpretations of those numbers, so that we don't just blandly accept them. Because actually, statistics lie. People can lie with numbers and data. They point a particular light on a fact from a particular direction to show you a particular picture, but you're not seeing the whole rounded figure. So you need to ask those questions. So it doesn't need you to be an ace mathematics professor, but it does need you to try to be able to be willing to ask those questions, even if, and this is something I tell my students, even if those questions seem like the stupid questions, they're often not. They're often the questions that everyone else is thinking of asking but hasn't been brave enough to ask. And if you're brave enough to ask the questions, then sometimes, hopefully, you'll get an informative answer. Right,
and you also talk a lot about Goodhart's law and this other thing, the Streisand effect. I never heard that term. I knew what it was, but I didn't know that there was a term for it.
Yeah.
But these are examples of where you get unintended consequences in part as a result of emphasizing or pursuing certain quantitative metrics.
Yeah,
right?
Yeah. These are sort of fun examples, I think, and mathematically speaking, I would call them examples of this sort of negative feedback. You try to stop something and it ends up making the problem worse. So with the Streisand effect, I think Barbara Streisand had this house on the coast of California, and there was some environmentalists who documented the whole of the coast of California to document coastal erosion, and they put all the photographs up on their website, and she'd seen these photographs of her mansion there and wasn't very happy about it. And so she tried to sue these people to get them to take it down. The point when she filed the lawsuit, only 6 people had been on the website and seen the photos, and at least 2 of them were her lawyers, right? So 4 other people had seen them. But by making this lawsuit, she drew huge attention to the fact that photos of her house were online, and then millions of people went to see these photos. So these unintended consequences, the examples of negative feedback. I think they're amusing, but they're also things that we should be aware of. In India, when the British controlled India, they had a big problem with cobras in Delhi. And so they decided that they would put a bounty on the head of every cobra that was brought to them. They would pay some money to the people who brought them the cobra. So obviously enterprising people in India decided they were going to start farming cobras. So they would farm cobras and they would kill them, and they would make loads of money out of doing this. And then the British got wise to this and decided to stop paying the bounty. And then, of course, the cobra farmers released all the cobras, and the problem was much worse than it was at the start. And so often these effects, these unintended consequences, are called the Cobra effect in homage to that story of the colonial British making a mess of things in India.
Now, I've heard it as the colonial French with the rats in Hanoi.
Sure, yeah.
Similar.
It may be the same. I don't know about that one, but certainly it may be the same story for sure.
Right, and then you also hold on a second. I just lost my train of thought here, so we'll
that's fine.
We'll delete that. So I also teach a course on game theory, and it's interesting. I could never make sense of whether game theory was a branch of mathematics or a branch of operations research or a branch of economics.
Yeah.
I mean, there are these disciplinary overlaps. John Nash was, I guess, he was a mathematician. But of course, we think of him as an economist.
Yeah.
And of course, in biology, game theory is taken over, right, in ethology and evolutionary biology. Yeah. Do you think? Game theory is something I think that everybody ought to have a rudimentary understanding of. Do you think of game theory as a branch of mathematics, or is it sort of something of biology?
So it's interesting because the one discipline that you didn't mention is psychology, and I think game theory could definitely be considered as a branch of psychology. It's about understanding how other people are going to react in certain situations, given that we assume that they are rational actors. It's about understanding payoffs and trade-offs and costs and benefits. Is it maths? Yeah, I think it's maths. I think John Nash would have called himself a mathematician. He sat in the maths in Fine Hall in Princeton, I think. But he won the Nobel Prize in economics, and certainly game theory has found many of its most famous applications in economics and in biology. I would call it mathematics. I think the underlying mechanics that are undergoing game theory, the theory is in understanding what Nash equilibria are, understanding all of these different ideas in game theory is mathematics, but I think certainly it's found most of its famous applications in areas, that are applied. It's a very applied piece of mathematics, in the same way that, we still call many things mathematical biology, but actually a lot of it you would just see as, for example, medicine nowadays. The way that we use artificial intelligence in medicine, that is mathematical biology, but actually that particular type of mathematics has found some of its biggest applications in medicine. So I think it's interesting, and what I like about mathematics is the fact that it crosses disciplines. When I went to university, I thought that I had given up on the biology and the chemistry and the physics that I'd done at school in favour of mathematics. But then when I got into my third year, I found this course called Mathematical Ecology and Biology. I was taught by this amazing professor who went on to be my PhD supervisor. And I found that I could use mathematics to apply it to different disciplines. So I don't think it's I wouldn't try and say that it's one thing or the other. I think the great thing about maths, and what I tell students when they come to applying to university, is if you apply to do mathematics, it only keeps doors open for you. It doesn't ever close any doors, because you can always jump back out of mathematics into another discipline, into physics or chemistry or engineering or whatever it is you want to do afterwards. But a good basis in mathematics at university means that you can go on and do almost anything you want, I think.
In business schools, we have this division between the poets and the quants, which I think is overstated and exaggerated and largely mythical. But it does seem that there are some people that are turned off by math, or they think they're bad at math because they were frustrated by trigonometry and calculus when they were in school.
Yeah.
But I find often that the people who think of themselves as poets often have a better understanding of some of the intuitive aspects of math and inference. Do you think that we turn people off on math early on by pushing them down this road that is, fairly rigorous, right? By saying, okay, we're going to have you study trig and calculus, and if you're not good at that, then you must not be scientifically minded.
Yeah, I think the way that we teach mathematics is difficult. I think there's a lot of emphasis on fast recall and on getting facts memorized, and certainly at university level memorizing sort of difficult proofs. And actually, for me, that's not really what mathematics is about. Mathematics is a much more creative process. And I've got two kids who are 10 and 8, and I really don't want them to be put off doing mathematics by the fact that they have to recall their times tables. And they have to do one question every 6 seconds for 3 minutes. And if they don't get 25 out of 26, then they're labelled with, you're failing at maths. And we've
got calculators for that.
Right, this is awful. This is not what maths is all about. Maths is a creative discipline. Sometimes it involves stewing and thinking about things. And it involves, in my case, it involves applying mathematics to the real world, and building models of the real world is a really creative process, because you've got to decide which bits you want to keep and which bits you can throw away, which are the most essential parts. And that's not a thing that you do in 10 seconds. This is something that you have to think really hard about and try and do trial and error and get things wrong, right? We don't encourage people to get things wrong enough. Getting things wrong is the way that you learn how to get things right. And this, in modelling, we go around these cycles. When I'm doing a mathematical model of a biological process, we go through this process of model, predict, test, and alter, and then you go back. So you build your model, and then you make a prediction, and then you test it against biology, and it's not right, and that's good because you've learned something, and you go and change your model, and you make a new prediction. You go around this cycle, and this is how mathematical modelling works in general. But it's a really creative process, and actually forcing people down a particular route and saying, if you didn't achieve this, then maths isn't for you. I think that's really problematic, and I think it does put people who might flourish in different areas of mathematics, I think it puts people off.
Do you think that the advent of these more sophisticated modeling tools expands the scope of mathematics? I mean, I remember this was probably 25 years ago. I was in an operations class, and we were talking about the Monty Hall problem, and the way in which the instructor proved the Monty Hall theorem, I guess it is through simulation, right?
Okay.
And he had a difficult time trying to explain it using math, and so he said, well, let's just do a simulation. We'll try strategy 1, we'll try strategy 2, and see what happens. And it was only after people saw the results of the simulation that they said, oh, okay, now it makes sense. Then they went back and they understood the math. Because we can do create these complex models now, does that kind of expand the scope of math? I mean, because we don't need to have, closed form solutions or anything to, demonstrate the impact of various assumptions and interventions and so on.
Yeah, it's funny because you sort of hit on exactly how I do math. The way I do mathematics is much more akin to the way that scientists do science. We in maths, we have these sort of very rigorous proofs, proof by induction, proof by contradiction, so on and so on. But actually, we sort of joke, at least in my group, about doing proof by experiment, right? So we come up with a hypothesis of what it's going to be, and then we do a hell of a load of simulations on the computer to check whether our hypothesis is correct. And then if we're fairly confident of it because of the simulations, then we go back and then we try and fill in the gaps of why that is the case using the mathematics, which is exactly what you described with the Monty Hall problem. You show people that it is the case, you convince them that it's the case, and then it becomes that much easier to search for the solution. It's like when you're told to go and search for something in the cupboard by your partner or whoever it is, and you're like, well, I can't see it, and they say, oh, it's actually in the back left corner of the cupboard, and then you're actually much more motivated to search. You're like, oh yeah, there it is. Actually, when I'm convinced that you know that it's there, rather than just saying go and have a look for this, then you find it. Once you've shown someone that this is the case, then you can go back, and it actually becomes easier to find the mathematical steps to the proof of that particular theorem or hypothesis or whatever it is. So yeah, there's a huge role for this proof by experiment, I think, and turning maths more into science. And it doesn't work in every area of mathematics. Like, I'm not a pure mathematician, so I'm not going to advocate that this is the way forward for every area of maths. And actually, there's a role for rigorous mathematical proof, because actually there have been some hypotheses where it's been proved, the conjecture's been proved true for the first 200,567 cases, but failed on the 200,568th case. So there is a role for mathematical proof, rather than just saying, well, I've done it a lot of times and it seems to work. But there's a way of guiding ourselves through it, and I think with the computational power that we have the ability to do numerical simulations rather than analytical solutions. We have the power to do, to really use maths to understand probability better, to use simulation to understand probability better. That's certainly a tool that we should be using in our arsenal. We should be using it to help teach kids as well, especially because technology is more and more abundantly available in the classroom.
Well, sometimes you know something, but you don't have a name for it, and that when I read a book and I discover that there is a name for it, I get very excited. And so, you talked about these two different types of predictions, right? The epistemic and the
aleatoric, yeah.
Right, and that seems to be, those are the kind of predictions that most scientists are making, right? Something already exists or has already happened, but if your model is correct, then you will discover it when you go and look for it, right?
Yeah.
In that place. And the example, I think the way you explained it is, the lottery hasn't yet been run, or
right.
The lottery has been run, and
yeah.
in both cases you can make a prediction.
Yeah,
right?
Exactly. So yeah, you don't. It's like flipping a coin. If I give you a heads or tails coin and say what's it going to be, what's the probability of it coming down heads, you'll tell me 50-50. Okay, then I'll flip it, and I'll have it in my hand, and I'll say what's the probability. Now the event has happened, and that's a different sort of uncertainty. But then you can still tell me 50-50, and that'll still be the correct answer. I can even look at it. I know the answer, you don't know the answer, and the probability is still 50-50 for you. These are different sorts of uncertainty. Epistemic uncertainty is about uncovering truths which are already out there, whereas aleatoric uncertainty is about the inherent variability or uncertainty associated with the world. It's like the difference between doing the lottery and a scratch card, right? With the scratch card, whether you've won or not is already buried underneath that latex scratch pad under there, whereas with the lottery, before the draw takes place, that hasn't happened yet. These are two different sorts of uncertainty, and understanding those differences, I think, is quite an impactful thing to have.
Yes, that's a concept I'm gonna start referencing with the appropriate
Right.
name. And I guess last question I would have is, we've been mentioning the COVID pandemic, and you were drawn into some public role where you were impacting the public understanding and public policy around the epidemic. Do you think, in retrospect, we need to have better kind of channels between the scientific and the policymakers? So rather than sort of spinning it up ex post, we have in place, better capacity to tap into the kinds of expertise that are needed to address these kinds of problems?
Yeah, 100%. So yeah, when the pandemic started, I started doing my sort of solo efforts to communicate science around the pandemic, writing articles about the R number, exponential growth, and SIR models, and so on. Some of the stuff that I'd written in The Math of Life and Death in the first book. But then partly because of that, I'm occasionally going on the news. I got invited to join this group called Independent Sage, who are a group of scientists across all disciplines. So virology, immunology, mathematicians, public health experts, people who are experts in inequality and so on. I got invited to join this group, and they held a weekly briefing where we would discuss the latest scientific goings on, the latest numbers from the pandemic, and we would invite questions directly from an audience. So they would come on and ask a question to us, and we would share things through Twitter and through blogs and our website and so on. So I'm a radical. I'm an advocate for radical transparency in science. The reason this group was set up was because SAGE, the Scientific Advisory Group for Emergencies in the UK, was not publishing its minutes. Its membership was not clear, and so the public didn't know the scientific advice that the government was using to make decisions which were clearly massively impacting their lives. And my opinion is that if we expect people to undergo these life-changing decisions, then we should be making clear the science which underlies them. Now, I don't think it has to be the scientists who are doing the modelling or who are giving the advice necessarily who have to be doing the communication. It might not be, they may not be best placed to do it. They might not want to do it. They might be really busy, which certainly many of the scientists I know who are doing the sort of frontline response stuff, certainly the modellers, were working around the clock, working incredibly hard. But we should be making an effort officially. I think we were a sort of unofficial group because there was no official group, but we should be making an official effort to communicate the science directly to the public. And in this case, communication doesn't just mean broadcast. It means having a conversation with the general public, finding out what the public wants to know, what are the questions that are burning for the general public, and answering those questions and having scientific discussion. This is what we did in this group. We have scientific discussions live on air, and we disagreed about things, and we talked about the nuances, about uncertainty, and about the papers that had come out and the different opinions that people had. And so I think, there's a massive role for that when the next pandemic comes around, which it surely will, or with other crises that are facing us, like climate change, for example. There's a role for communication to the general public, with the general public, about science. And I think that's something that's coming out of the UK's COVID inquiry, is that we just weren't transparent in our scientific evidence, and our scientific communication was not good enough, and we made mistakes, and they were not picked up on because it was a closed system and no one was there vetting it. And so I think with better scientific communication, with people who are asked or employed specifically to communicate science, who are nevertheless experts in the field, but maybe not the frontline scientists who are doing the work, then we could get a much better response, both from our scientific response, but also from more buy-in from the general public. As this is the reason why you're undergoing these restrictions. Oh, maybe I understand that better now because I understand the science. Yeah, so I think it's really important. Scientific transparency is vital.
Well, do we need that just for emergencies? I mean, there are also, you mentioned climate change. I mean, there's crime, and there's lots of things where science has insight to offer. Should we be thinking of kind of replicating that model for a number of other public policy issues?
Yeah, I think it would be great if we could. I think the unique thing about the COVID pandemic was that, well, firstly, people were sort of a captive audience. They were sitting at home with not much else to do. And secondly, it was impacting everyone's lives so directly. Whereas climate change is obviously directly impacting people's lives, but in a sort of more passive way. And it seems like less of an emergency because it's not happening on the same time scale, right? It's an order of magnitude slower. But nevertheless, a huge emergency. But will you get the same public buy-in is an interesting question. But I think more generally, you talk about crime, talk about any policy that's made. What we hope for is that policy that's made is based on evidence, so that we have evidence-based policy. But unfortunately, what we're given all too often is policy-based evidence. Politicians cherry pick the evidence that they want to support their policies, and that's not the right way around. And I think more transparency about the science and the evidence that is underlying particular issues, with through fact-checking websites, whatever it is, can help us to hold politicians to account, to ensure that we get better evidence policy rather than allowing politicians to get away with cherry picking the snippets of evidence that they like to support their particular chosen policy.
Well, Kit, your love of math is obvious and infectious, and so we should check out How to Expect the Unexpected and the Math of Life and Death. Thanks so much. Chat again soon.
Thanks so much. Cheers, Greg.
unSILOed podcast is produced by University FM, elevating the stories of your institution.